Hello everyone, welcome to CYBR601, Introduction to Cybernetic Modeling and Simulation, Learning Activity 11, System Dynamics. And what's really interesting about system dynamics is this is really one of the major pillars of the degree for the Master of Science, the ISD program. And when you deconstruct the name of the Master of Science, Integrated Systems Design and Dynamics, there is a component where system dynamics is really getting into really complex phenomenon. It's we really wanted to impart a focus on nonlinear complex systems, and of course the design part was not just to emphasize just doing dynamics. In other words, the idea of maybe just analyzing the dynamics of a system or a complex system, but also being able to get in there and do the engineering. So hence why we created a design and dynamics degree. So anyway, that's a little bit of background. We're going to jump into more of the specifics around what is system dynamics right now. Okay, so system dynamics is a framework for framing, comprehending, and debating complex issues. It can be used quite a bit across a wide body of work, and system dynamics is really powerful. There's actually a whole PhD program at Massachusetts Institute of Technology that gets into it's actually a PhD in system dynamics, and that's all they do is just system dynamics. So it's a very comprehensive field. There's actually a conference, annual conference, the System Dynamics Society, and that supports this field from a research perspective, but also has people from all over that supports collaboration as well. So it's pretty powerful. It's not something new. It's actually been around for a while. The concepts of system dynamics was created back in the 50s, and has a little bit like machine learning, artificial intelligence. It's a little bit of a resurgence as of late, because it does incorporate a lot of different disciplines, and it's very useful in being able, as a simulation discipline. It's not there's a simulation component to system dynamics. System dynamics as a broader field has its own is its own discipline. But when we talk about system dynamics modeling, system dynamics simulation, that's a component within the broader discipline. So if you're interested in learning more about it, there's 3 references over here that are not light reading, but definitely worth taking a look at. We won't need that for us here because, again, we're an introductory, a graduate level introductory course to all things modeling and simulation. So we won't have enough time to just dive into all the intricacies of systems, system dynamics simulations. Okay, but what is let's jump into what it is, what it can be used for, and just all the different aspects of system dynamics. So here's a very interesting diagram. This was an actual system dynamics, or what was called it's an Afghanistan stability dynamic model, and this was actually created. You can go out. I put the link up in the upper right hand corner. It had some criticism when it first came out. This was years ago during, of course, the conflict. But this can show you. This is actually a perfect example of how complicated a system dynamics model can become. Now, I don't know that in this particular case that it's available for everyone here to. I don't have an interactive version of what it is that happens here, but you can see that it gets complicated pretty quickly, especially when you look at something when you're trying to do system modeling out a complex system as it relates to something like Afghanistan. we'll be doing something interactive at a much smaller scale. And let's talk through what those how, in other words, how do we get to, that's kind of the goal, is how do we create something simple, a simple system dynamics simulation through what we're going to be learning here today. So to do that, we need to learn about what are the major components of a system dynamics model. And well, first we have causal loops, and then we have stack and flows, and then we have equations. And you'll notice quite a few things going on with the way that shared shared concepts from other lectures make their way into this, and you'll start to get a feel for like how comprehensive system dynamics can be. Okay, so first up, we've got causal loops. And causal loops, or actually there's a whole, if you're interested in looking it up, there's a whole thing on giant Wikipedia page just on causal loop diagrams, or CLDs. So CLDs are kind of broken up into two components. There's loops and links. So loops, there's really two major, in system dynamics, there's really two major components. You've got reinforcing loops and balancing loops. We're going to focus on, actually, for the U-try exercise in our lab, we'll talk a little bit about this towards the end of the lecture, but we'll focus on creating a balancing loop. And then there's links. There's positive, negative, and there's link delays. There's also neutral, and I'll actually have a definition for that too. But know that you've got positive, negative delays and neutrals. Now, because a lot of you are in the machine learning and autonomous systems track as it relates to ISD, these loops, the reinforcing loops, as well as balancing loops, the links, these are visual representations of actual things that we have to cover in machine learning. And this is something we'll talk about more as we move along. But in statistical analyses, anytime we have two variables and we're comparing one variable to another, and I'm keeping it simple for the conversation of what it is that we need to talk about here for this lecture. But if variable A and B are proportional in their growth, in other words, as A increases, B increases, that would be a positive link. And again, I'm not getting into the differentiations between like a logarithmic increase versus exponential. I'm just saying a general increase. So a general increase in one in A leads to a general increase in B. That's a positive. When they're inverse, so for example, when a variable A increases and B decreases, that's a negative link. And then in system dynamics, it takes it a little bit farther than what you would kind of cover in a statistical sense, in that you have to model out delay links, or linked delays, or a link in a link that has a delay, so to speak. And this is important because, like, for example, like logistics, when you're modeling out a supply chain, right? I mean, there's going to be delays. Things rarely model themselves out in a logistical sense, and not there's just not going to be a delay, if that makes sense. And then finally, there's going to be this concept of neutral, when I say neutral here in the sense of system dynamics, we're actually talking about a link that has a cause with no effect. That when and we'll see this actually happening. This is something that I'm going to actually have you model out, where a cause has no effect through a series of events, and that would be called to a certain extent a balancing loop in this case. One more piece of information is that there's because the system dynamics work so heavily within a loop system, it's very cybernetic heavy. So the concepts of cybernetics and the concept of transformers and the concepts of machines, they all are still very much the what's happening in the system dynamics world. Borrows heavily from cybernetics, and and so you can see a lot of shared history there. All right, next up. So loops and links. So I talked about these. Here's more detail. So this is just jumping into the specifics. Positive, two variables change in the same direction. Negative means that as one variable goes up, the other one goes in the opposite direction. So when one goes positive, one goes negative. When one goes negative, the other one goes positive. Neutral. This is where there's no where the cause has no effect. And then I talked about delay, and then a little bit more just a textual definition for reinforcing and balancing. One thing that's an interesting phenomenon that you will see in the exercise, the lab, is that a balancing loop, as it relates to the system dynamics simulation that we're doing, they're kind of easy to spot. I mean, outside of course, having a contradiction in the initial state versus the final state, or something that is deviating from the initial state from what you're expecting in the final state or the final variable. One way to spot these balancing loops in the technical term of the system dynamics world is that they have an odd number of negative links. So that's one thing to keep in mind. Okay. So stocks and flows. This is another piece of system dynamics that system dynamics can be complicated. It is complicated, but it doesn't have to be for very basic small simulations, which is what we're going to focus on for our lab. But for us, stock and flow models, they look just like this. It's a easy, if you look at the stock and flow over here, I've got a flow of new investments coming into. If you look at the square on over here, right over here, this square, think of this as kind of like maybe a good way to think of this is like a portfolio. So this is your stock portfolio, and let's say you're managing a portfolio, a mutual fund for a group of investors, and then has a stock. It has capital inside of it, right? Which is the equity that has been. You have when flow of new investments. You can think of as inflows to the mutual fund. And so as the if inflow increases, right, this increases, then the stock of the capital, right, your mutual fund should increase, right? But you have to balance that out with depreciation or depletion of the outflow. You have outflows within a mutual fund. So as you have inflows, you'll have outflows, right? People redeem their mutual fund. They'll sell their mutual fund positions, and then they'll cash out, and that's what's called an outflow. So that's what this is a good example of using system dynamics here. It's a very simple case of inflows versus out. Now I will say that there is what tends to be the problem when you're looking at, or at least I shouldn't say problem, but which tends to be a very first common mistake when you're doing system dynamics modeling, especially when you're looking at stock and flows, is that the stock and the flows are they're independent. They have independence rather. So in other words, the incoming money doesn't necessarily have to flow with outgoing money. In other words, just because I add money to my mutual fund doesn't mean that there has to be an outflow. There's gonna be. The system naturally has some kind of variable for outflow, but it doesn't. It's not dependent on an outflow, if that makes sense. So you can, and this is what happens with big mutual funds. They accumulate a large amount of money, and actually that's its goal, is to increase its assets under management. And I'm just using investment strategy because it's an easy one to think of. And minimize its depletion or its outflows. So in other words, one isn't necessarily requiring a balance in that, and that's probably the better way to say that is that there isn't this ratio, hardened ratio balance between inflow and outflow when you look at stock inflows. Okay. Let's talk through this. So this is textual definitions, stock, and then we talked about what that looks like, flow or the rate, and this is the lines, and we won't be able to necessarily model that with the freebie modeling tool we're going to use. We will be able to model out stocks, but not necessarily the flow rate. But one thing to keep in mind is that every system dynamics model has some kind of time dimension. You can't do system dynamics without time. They must be, whether it be discrete or continuous, the stock and flow process between in a system dynamics model, it is time bound. I'd already talked about this. The upper right hand bullet rather is that stocks and flows can differ, but this is just a more technical definition. So I talk about it in terms of topology. So a stock and a flow can have differing structures, differing topologies. So just in other words, they can differ in their structure, but they can also differ in their time. The timing events between the two aren't hardened, aren't connected in a they're loosely independent. That's probably a good way. That's probably the best way to explain that. Okay, now that I've completely confused everyone, it's probably easier. You'll see it in the lab. Things will make a little bit more sense when we get there. So, but for us, let's talk a little bit about these. Not just now that we've kind of gone through the components. That's kind of the high level components when we talk about the causal loops, balancing, reinforcement, positive, negative links, as well as the different, as well as stock and flows. Whew, I knew I was going to eventually get there. When you look at the underlying mechanisms of an advanced system dynamics simulation, there are elements of everything that we've talked about to date. There's numerical simulations, there's agents, there's entities and attributes related to those entities. There's also discrete, if we're talking, there has to be a time component as it relates to the SD and SD sim. But it can also be continuous. That's what's kind of neat about system dynamics. You can have parts of it that are discrete, parts of it that are continuous. You can have parts of it that are stochastic, parts of it that are deterministic. And it can also include numerical simulations. So SD sims, very complicated SD sims, usually have some kind of equation, whether it be an economic growth model, whether it be some kind of epidemic, what's the word I'm looking for? Epidemic growth. In other words, some kind of logarithmic growth to a disease model, or a virus spread, something like that. If it can be numerically, if there is a equation at its core for the spread of, let's say, information or whatever, right? A distance function as it relates to like an agent-based model, then yeah, it's got everything in it. So system dynamics, especially when are really large models, can get pretty complicated really quick. Now, in our lab, I'll show you something that's, both of them are going to be pretty pretty, I'd say pretty straightforward. One of them is probably a little bit more complicated, and then we'll create something that's real simple, and then I'm going to actually have you create something for the you try lab. So just know that when we're talking about system dynamic simulations, it can incorporate everything that we've talked about up to today. All right. So the simulation architecture for this is something that's a little it can incorporate what I just talked about, which is a lot of different elements, deterministic, stochastic, and all the other fun stuff in there. So I just kind of tagged that as a hybrid in the simulation architecture, and it can incorporate all components. Time is very much at a core of what it is. You can't get away with doing SD without time. Loops and links and stocks and flows. They go just like before, computer hardware, operating system, M&S software, all that goes into the sim. M&S software is going to be different this time. We won't be using Python. This is going to be a non-coding. It's going to be somewhat similar to the Microsoft Make code that we did in the beginning of the semester. The Starfield generator and running through that, but this is going to be it's going to be a drag and drop kind of a block coding kind of strategy, very similar in that respect. So that's a different M&S software we'll be using, so with that, I guess is a good segue over to talking about the lab. So in the lab, we're going to be doing something abstract. I'm going to show you something that's real world, but then for the you try portion of the lab, you're going to, we'll create an abstract framework so that we can focus on the relationships, and then we'll focus on creating or illustrating a balancing loop. So that's why I want to in this case you'll get a feel for like a real world example. Actually, we're going to use an epidemic vaccination actually as it relates to what we're trying to do. It's going to be a vaccination related to an epidemic, and then what are the effects of vaccinations or vaccines in a vaccine program, and modeling that out. What we're going to do in the U-Try, that's going to be for the follow along, but for the U-Try, you're going to have a more abstract dynamic, and one just to kind of keep it simplified, but also to make sure you're focused on just the fundamentals of what it is that we're trying to teach you for system dynamics. Okay, so this brings us up to week 5. So congratulations, we are past the midway point for this course. Follow along. SD simulation is what we're going to be doing. Make sure you're keeping up with the Canvas modules. Everyone's been doing great. Look like everyone crushed the last 2 quizzes, so keep up the good work. And then a couple things to keep in mind for the lab that we're going to be doing here in just a minute is, or rather coming up here, is a few questions. How many negative links did you create? And this is for the U-Try section of the lab, and just thinking through the end variable versus the start variable, and how did the end variable move as in relation to the starting variable? So that's something I want you to keep in mind, and in your case I'd like to know. And then what would you differently to make it a reinforcement loop? And so what I mean by that is we are working on creating an abstract balancing loop using Sage Modeler, and we will do that, and you will do that. But I would be curious to know, like, what would you do to make it a reinforcement loop? Make sure you know this, because again, this will come up in your final quiz number 3, and then that'll be the last quiz that we take. So 3 quizzes, and then after that you'll be focused on your final paper. And in relation to your final paper, continue on with your readings. In this case, you will finish up the NSF paper. It's a short read for the final, is 53 and 57, and this kind of focuses on opportunities for the future for simulation. Now, remember, this was written in 2006. So some of this is, and this is some partly what I want you to be thinking about as you're going through as a source for your paper, because this is a reference, revolutionizing engineering science through simulation. So this is a source for you for your paper, but there are many, many other sources. So, all right. That's a good segue over to the final project. As promised, I said I'd talk a little bit more about each of the pieces as it relates to your paper. And so I am going to move over to Word. All right. And so I want to talk about this guide. So this is the final research paper guide, and I've already talked through all this. So I do want to give you a refresher, and then I'm going to focus on a couple things. So two things in particular. All right. So you need a research title. You need an abstract. You don't need keywords. You need an introduction. You need a research goal, background, a background section. You do not need a hypothesis. You do not need the methodology, results, or discussion. You don't need those for this paper. You will, however, need that for your thesis. This is all very much required for your thesis. So when you get closer to being ready for that, of course, we'll help you through that. What you will need for this is this final research paper is you'll need limitations, conclusions, and references. Okay, so there's this this outline, and then of course I gave you a template as well for you to work through. There's one thing that I want to help you with as you go about your research and looking for references. So I kind of gave you a topic or an area to research, which is comparing and contrasting simulation techniques and or architectures. So you've got some you've at least got some guardrails, right, to keep you on track in terms of how to approach this. Now, two things I want you to be thinking about is the research goal. So one of the best ways to work on a paper, and this is also true of your thesis, is I like to start in the middle and work my way out. So in other words, I'm kind of it's hard to write a paper when you start off at the top with a research title and an abstract and then an introduction, right? It's kind of hard to go 1, 2, 3. It's just really difficult. You're better off starting in the middle and working your way out. And the best way to do that is establishing what it is what is your research goal? What are you trying to do? In this case, you might be a couple different things you might be asking yourself is, well, if I'm comparing and contrasting simulation architectures, what specifically are you contrasting? Are you contrasting numerical simulations versus agent-based simulations? Or are you comparing system dynamics with contrasting system dynamics with numerical simulations? Or maybe you're interested in doing discrete event simulation versus something that we haven't talked about and we won't be covering for this course. And it's an open area, which is discrete event simulation versus continuous event simulation. So these are some areas that you can focus on for your research goal. And the best way to do that is just ask yourself what it is you're trying to do. What's the research question? Okay. So once you have that, so let's say I want to get creative and I want to take the harder, I guess it's not necessarily harder, but the path of continuous event simulation versus discrete event simulation. The best way to get started on your paper is write down that goal in Notepad. That's my favorite way to go, is just go and say, get your Notepad out. It's an open space. And what I like about Notepad is it's got this entropy, this very, very low entropy environment. Whereas Word is very high entropy, but you got buttons and ribbons and all kinds of stuff. You end up feeling like you got to formalize a document right away, which can confuse people. That's why I really, because you're like, where do I start? Because you immediately go into the thought process of, well, I've got to formalize a document because I'm opening Word up. Of course, I have to write something that's formal. That's why I always recommend start off with Notepad, because it's simple, it's easy, and it keeps you focused on just the content. You're not worried about anything else. You're not worried about formatting. You're not worried about any of that stuff. First thing you want to do is, what is my research goal / objective, right? And I'm gonna start one off. I'm gonna say, hey, and you might have two, you might have a couple, but I'm gonna start one off and say, for what I'm trying to do, I'm gonna say, compare and contrast discrete event simulation versus continuous event simulation. Okay, and that's plenty. Okay, and then the next thing you want to say is, where do I go to get content for my paper? Okay, right? That's valid. Okay. Well, if we're comparing and contrasting, compare and contrast discrete event simulation versus continuous, and you don't have to be all very specific. I probably want to do, because I'm comparing and contrasting, I probably want to say, okay, what references, what literature exists for DES? What literature exists for CES? Then compare and contrast. Okay, so this kind of rough sketch, rough outline, right? And remember, go back to you're working in the middle. You're just working on the content. You're gonna be learning more about this. Okay, so once you get your kind of discrete versus event, versus continuous, one thing that you'll want to make sure that you that you use is Scholar. So make sure you go to Google, scholar.google.com. And this is a great first place, one of the best places to go. There's going to be more that we're going to show you. There's a lot of different research repositories, but scholar.google.com is the best place to go right up front in terms of getting started for a literature review. And that's kind of what we're doing right here. We're not asking you to create a research. We're not asking you to create a hypothesis. We're not asking you to establish your methodology. We're not a research design. We're not doing the analysis and the discussion, and we're not asking you to go through all that. This is just really, for all intents and purposes, this is a kind of a literature review. But with a little extra to it, right? We're doing a compare and a contrast of differing architectures through a literature review. Really, kind of two is a literature review on discrete event simulation and a literature review on continuous event simulation. So the next thing you want to do is just let's search on discrete event simulation. So we'll do a search on that, and then this is where you're going to find all kinds of fun stuff. So this is probably a really good one to work with. It's from 1986, discrete event simulation distributed, and then ACM.org. When it has a PDF like that, that means it's free, and I highly recommend going that route. So what you want to do is take all this information, and then you're going to see a lot in here for discrete event simulation. And to do this right and to do this properly, you've got to read everything that you cite. So this is a good one. Just looking through this real quick high level, that's a good one. What you do is, let's say I'm going to use this one as one of my base papers for my research. Go click on this, and then here's an APA link right there. And then you can copy that and go on and head back over to over here and just put a, for the purposes of what you're trying to do, save all your references off. Okay. So let's say you like this one right here from 2010. It's available on ResearchGate. Grab that one. And remember, these have to be in order. Alphabetical order. So your APA references, if you stack them up in alphabetical order ahead of time, it's going to save you a ton of time. Let's see. I'm going to run down through, and then you get a little bit here. There's just a little bit of a blurb on this. This looks, this might be useful. Who knows? Healthcare systems. For me, this is nice because it's nice to have use case related. So in other words, industry related simulations are useful because you can reference those in a non-abstract way. In other words, this is discrete event simulation theory, but then this is discrete event simulation applied. So this might be a good applied one, right? That might give us another talking point. Let's see, Jacob QRST P right here, Jacobson, right? And then you'll just keep going down through. Now make sure that you save these, like this one right here. Download that and save it. So as you start to build this up, you'll start to read through and get a feel for highlight the material, read the references. Just don't read the abstract, but actually read the papers and get a feel for what is discrete event simulation, and then start just highlighting high level. Here's the major components of discrete event simulation. You kind of already have a feel for that already today, right? Then what you're going to do is you're going to come over and do the same thing for continuous. So here's a perfect one right here, discrete versus continuous simulation. That's from 2009. I would probably want that right off the bat. And so that's one I'm going to pull in. And that's perfect. We can put that right there. Parallel discrete with application to continuous systems. I don't know. Discrete event simulation to continuous systems. Continuous system simulation. That looks pretty good from the continuous side. So I might go out there, pull this. Let's see. All right, there you go. Put that in there. Modeling continuous flow. No, probably not. You'll just discrete event simulation, continuous software. This one might be useful here. This is Simulink. That's some software. IEEE. That's always a good one. So you might want to double check this. That might be a good one. B. And I'm going to stop there. So the idea here is, as you start to build up your references, you're going to go and read those, and then you're going to put the body in. You're going to start talking about what literature exists for DES, and then you're going to list out, this is what they said in Babuluk, Bochima, Sellier, Jacobson, right? This is what they said about these different areas. And then what you're going to do on this compare and contrast, that's you imparting your piece of it into what you thought were the differences between DES and CES. And so you'll just keep iterating on it. You'll just keep building on this. Another note, too, that might pop up for you is, as you're going through this, especially for literature reviews, you'll find stuff that's from the 70s, 60s, 40s, 50s. Sometimes if you're getting reference, if you're jumping into the math will go back into the 1700s sometimes, depending, especially for machine learning and you're doing Bayesian analysis. You can't do that without Thomas Bayes from the 1700s, right? So where I'm going with that is it's absolutely okay for literature reviews to be using old references. There's nothing wrong with that. I actually suggest that you do as far. I actually suggest that you push the envelope and go as far back as possible, because there's a lot of good nuggets in a literature review if you push the boundaries and try to go really far back. I mean, and really dig deep and think about it. Um, like for mechanical engineers, you can go back to easily back to or civil engineers, right? You can easily go back to Egyptian Roman times for a lot of especially the Romans. They've made concrete that is still in use today. Um, and still under research today. So that's a perfect example of it's very useful, especially for the literature reviews, to go back that far. Now there is a point where in your references, or if you're writing a paper, that you do, depending on the type of paper you're writing, that you want to keep it current within the last 10 years, because sometimes it's more important for that to occur. But in this case, you definitely want to push the boundaries and go back as far as you can on your references. Okay, so with this, I'm gonna leave this up here for the recording. Feel free to pause it so you can grab these. I will talk more. That wraps up what I want to talk about for the lecture. But I did want to spend a little bit of time just going through and talking through a little bit more around how to approach the research paper. I will be doing probably one more session on the research paper, just in the interest of time. I don't think I'm going to be able to do another one. So I'm sorry, let me rephrase that. I will be able to do one more, and then outside of that, I won't be able to do another session because we need to give you time to actually write the paper. But if you have any questions, Dr. Jackson or myself are here to help, of course, with anything related to your final paper, or the quizzes or anything else that might pop up. So with that, one last thing I do want to mention before I sign off is this week is week 5. Next week is Unreal Engine and model-based systems engineering. So we'll be doing MBSE as well as full world model, or what I call world modeling or world simulation. I don't know that there's an actual term out there like that, but when we start getting into gaming development or world modeling, you kind of, whether it's a first person shooter, whether it's a third person, whether it's a racing game, there's a world that all those usually exist within. So world simulations are, of course, the pinnacle of simulations. They're really up there in terms of, I mean, they include everything that we've talked about today, up to this point. So we'll be doing that, and once we hit week 6, though, and you wrap up, I'll be handing the reins of the course over to Dr. Jackson for the final 2 weeks. He'll be going through a lot of fantastic material, and adding in control systems, and talking about simulation as it relates to control systems for the final 2 weeks. So I'm really excited to be bringing him in, and I'm excited for you to be getting some exposure from and some MNS exposure rather, to his background. So all right, with that, I'm going to sign off on this lecture, and I will see you in the lab.